So, barely even a few weeks into the school year, and you guys are already creating this? I'd say that's pretty good. But what's exactly going on here? Let's take a moment. I want to talk to you guys about something called Bohr models. Now, we've had an introduction before, but let's really understand it right now.
Now, in order to understand anything about matter and atoms, we'd have to go back and look at how each of these different scientists contribute to our knowledge and understanding of the atoms today. However, in this video, we're not going to do that. We're instead going to skip to a specific scientist, Niels Bohr. Niels Bohr had an atom model a lot like what we're familiar with today. People knew about the nucleus with protons and neutrons inside, as well as electrons floating around the outside. They called this the solar system model, and these are the ones you might find in a typical science textbook. However, Niels Bohr was very unhappy with this model. Something seemed wrong about it, and he wanted to figure out what it was. Around his time, there were many scientists who were studying things called spectrums or light spectrums of different elements. This is a light spectrum of helium. What scientists would do is they would ignite helium under a fire, look at it through a prism, and they'd look at the spectrum lines, this red, orange, yellow, green, blue, indigo, violet color, as you'd see through a prism. Scientists noticed that in certain elements emitted certain spectrum more than others. For example, you can see here that there's this red line, kind of a blue line, and a purple line that really stand out. This was true for all elements. They all had their kind of own special signature. You can see here hydrogen has its, helium, lithium, oxygen, each had their own spectral lines. Niels Bohr saw this, and it really helped solidify a new understanding of what an atom might actually look like. Niels Bohr came up with something called the orbital theory. He stated a couple things. He said that electrons, instead of floating around like planets in a solar system, instead are confined to specific orbitals around the nucleus. Secondly, he said that electrons can become excited, they become charged, and they might be able to jump orbitals. Eventually, these electrons will relax and fall back down to the previous orbital or a low orbital, and in doing so, they'll release that stored energy. It's this information that helps us determine the different wavelengths of light that substances can emit. Let me give you an example. Here's a little animation. You can see here that the electron will absorb a certain wavelength of light. Now, after that electron gets excited, it actually releases that same wavelength of light and falls back down to a lower energy state. Here we see the electron absorbing red energy. Now again, it could be absorbing much of all energy of the sunlight, but it's specifically releasing red. This is shown in our flame test lab, where we see lithium or strontium releasing red light, and that's why we see that. It's because strontium emits that light, where the electrons do in the Bohr model. Another example is sodium. Here you see that a sodium atom, as it absorbs certain wavelengths of light, will eventually release those same wavelengths and show yellow-colored light.
Now I want to take a moment and show you the atomic spectrum in action in real life. So in a second we're going to pause the video, but in the meantime, we need to exchange our glasses for a pair of these. And then we're going to show you this. So take a moment right now and pause the video. Push the button in the corner. We're going to pause this video. Turn off all the lights. Yeah, you, right there. Right there. Yeah, you. No, not you. You. I want you to go ahead and close the blinds as much as possible. Now you on the other side, you go and get those blinds over there. Turn off the lights, all of them. Turn off the projector. We want to get it as dark in here as possible. After that, put on your glasses, take a look, and slowly, one by one, we're going to go ahead and turn on each of the different spectrums using the spectrum tube. When you're done with that, when you've taken a moment and looked, we're going to come back. You can go ahead and turn everything back on and unpause it, and we'll continue from there. pretty neat, right? Well, it's all attributed to Niels Bohr and his understanding of the atom. Through his logic and his equations, we were able to figure out exactly where the electrons were jumping and what wavelength of light they were emitting when doing it. And he did that using the hydrogen atom. This is really neat because we use this type of information all the time. If we know the electron spectrum, it's a lot like fingerprints in DNA. So even in chemistry, we have forensics, but not forensics just for people, forensics for everything. Everything around us, all the elements, including the stars in the sky.
That's right. Spectral lines really are like fingerprints for atoms. For example, if we were to get the spectral line of something, let's say the sun, then we would know what the sun is made out of. And in fact, that's exactly how we do. We can't take samples of the sun, but we can see its spectral lines. So just to reiterate, electrons must reside in specific energy levels, and these are called orbitals. So here's some examples. The diagram that you see here is called the Bohr model. Just to let you know how to draw Bohr models, let's begin our journey in doing so. The periodic table will help you because each row of the periodic table determines how many orbitals each atom has. So the first orbital, or the first row, has one orbital. The second row, and all of the elements in the second row, has two orbitals. The third row all has three orbitals, so on and so forth. One thing you need to remember is that a neutrally charged atom has the same number of protons and electrons. So in order to draw the electrons in there, know that however many protons there are, you have the same number of electrons. So now that you remember this, let's go ahead and try making a Bohr model. So let's start here with helium. If we look on the periodic table, this is the information that we get. What can we pull from that? Well, helium is in the first row of the periodic table. Therefore, there's one orbital. Looking at it, we know that helium is made of two protons, and therefore, because it's neutrally charged, it has two electrons. Because it's on the first row, we're going to put both of those electrons on the first orbital. And that's it. We're done. Let's try another one. Let's look at nitrogen. So nitrogen looks like this on the periodic table. It's in the second row, which lets us know that there's actually two orbitals we need to worry about this time. The atomic number 6 lets us know that there's 6 protons, and therefore, being neutral, we need to realize that there's 6 electrons. Now the first orbital has to hold the 2 electrons of the 6. Remember, the first row has 2 atoms in it, or 2 elements. Therefore, the first orbital has 2 electrons that go in it. The rest of the electrons go in the next energy level. 1, 2, 3, 4, and then that makes up the rest of the 6 with a 2 in the middle. That's it. We're done with nitrogen as well. Just in conclusion, let's go ahead and review what we know. First, electrons reside in certain orbital energy levels. Second, you should also know how to draw Bohr models by using the periodic table.
Alright peeps, that's all we have for you today. And remember, chemistry isn't just a bore. It's pretty awesome as well.